Hello there, Mr. Sutton here, bringing you the Algebra 2 7-1 lesson on inverse variation. In this one, we will be determining whether a relation varies directly, inversely, or neither, and we're going to be writing some equations for variables that do vary inversely. To start us off, let's get a few definitions out of the way. So first off, this idea of variation, we're basically talking about how a change in one variable affects another. And there's a few different models we can follow. The two we're going to be looking at today are direct and inverse variation. So direct variation means an increase in one variable causes a proportional increase in the other. So that means that we can express this in the form of y equals a times x, where a is the constant of variation. So basically, as x increases, there's some multiplier that we multiply that by to get y. Now, the other type of relationship is inverse variation, where an increase in one variable causes a proportional decrease in the other variable. And these can be written in the form y equals a over x. So a is some constant. And notice as x gets bigger and bigger and bigger, y is going to be getting smaller because you're increasing the size of your denominator. So with that theory out of the way, let's do a couple problems here. In this first set of problems, we're going to tell whether the x and the y in each of these three equations show direct variation, inverse variation, or neither. And the idea on all of these is basically, if you look at the two forms here, we have a y equals kind of situation. So if you can isolate y and see if the equation can be put in your direct or your inverse form, that'll tell you which type of relationship is going on. So pause the video and try all three of these. All right, so let's look at part A here. To isolate y, on this one I have to divide by x, so I have 5 over x. That's in a over x kind of form. We have a constant over x, so this would be an example of inverse variation. Next up, we have y equals x minus 4. Y is already isolated here, and it's not in either one of these forms, so this is going to be neither. And for the last problem, to isolate y, we have to multiply by 2. So we have y equals 2x, and that's going to be ax form, so this is going to be an example of direct variation. For this next couple sets of problems, they want us to tell whether the x and the y in the tables shows direct, inverse, or neither type of variation. So here's a little trick you can use with x's and y's to see what type of variation we have going on. Let's take a look back at the last set of problems we did. So these were these three problems where we were trying to figure out what type of variation it was. Now you notice the one where we have inverse variation, you have a product of x and y equaling this constant here. So when x and y are together, they equal a constant when you multiply them. Over here with direct variation, if I wanted to, I could switch this 2 and this x and write this as y over x equals 2. So we would have the quotient or the ratio being a constant number. So the idea then, just to kind of summarize that, if x and y have a constant ratio, they're going to vary directly, y over x type of situation. Contrary-wise, if they have a constant product, then they're going to vary inversely. So pause the video, test those possibilities out, and let's see what you think this is. All right, so I'm going to set up a little table where I take a look at what happens when I multiply x and y and when I divide x and y. And the ratio, it's not actually really going to matter if you do x over y or y over x, but I'm going to do y over x, just because that's how it would have been written on that last problem there. So going through and multiplying these, 2 times negative 12 is negative 24. 4 times negative 6 is negative 24. 6 times negative 4, negative 24. And 8 times negative 3, still negative 24. So this is a pretty strong case for, since we have a constant product, it looks like, inverse variation. But let's just check the other way just to be sure. So negative 12 over 2 is going to be negative 6. Negative 6 over 4 is not negative 6. We could write that as negative 3/2 if we want. And once we break the pattern, we don't have to keep going. So we see here that the product is constant, the ratio is not. So constant product, that means we have inverse variation. Let's do one more of these table sorts of problems. Pause the video and try this one out. All right, so setting up my table with x, y, and y over x, let's do the products first. Those are the easiest ones. So 1 times 2 is 2, 2 times 4 is 8, and we don't have a constant product. We've already broken that pattern, so it's not going to be inverse variation. Let's see if it's direct variation. 2 over 1 is 2. 4 over 2 is 2, and you're thinking, okay, this might be direct variation, but you have to keep going, right? Because we could just have a coincidence with just two numbers there. 8 over 3 is not 2. It's still 8 over 3. So that pattern is broken, and it turns out we don't have a constant product or ratio. They are both not constant. Therefore, this is neither direct nor inverse variation. On this next problem, they're telling us the variables x and y vary inversely. They're giving us that. They want us to use these given values of 3 and 4 to write an equation relating x and y, and then find the y value when x equals -2. So the key here is to use that inverse variation form and basically plug your x and y into that y equals a over x form. That will allow you to solve for the a, and once you've got that, you can actually write this equation and use it to find whatever you want. So pause the video and see if you can execute that, and we'll bring it back in a moment. All right, so let me write this out, y equals a over x, just to have it written out in a fancy kind of fraction form. And now let me substitute what I've got here. So my y value is 4, and then we're going to have a over the x value 3. And then solving for a is pretty easy, just multiply 3 times 4, so a is 12. So then we can write y equals 12 over x. So that's the equation that they wanted relating x and y. And now if I want to find y when x is -2, I can just plug -2 into this. So we have 12 over -2 giving us our y value, which is going to come out to -6. For our final boss battle problem, we're going to do one that's kind of like the last example, only to a much higher level, higher extent. So the time in hours that it takes a group of volunteers to build a playground, like this beautiful one here, varies inversely with the number n of volunteers. So we have some n that we're plugging into a function, and that gives us a time value back. So volunteers is the input, time is the output. Now they're telling us it takes a group of 10 volunteers 8 hours to build the playground. They want a table showing the times it takes to build our playground when we have 15, 20, 25, 30 volunteers, and they want to know what happens to the time it takes to build the playground as the number of volunteers increases. All right, so let's first off pause the video, see if you can write an inverse variation relation that ties together this 10 and this 8, and then see if you can use it to find these different table values. So I'm going to use my general form, but instead of writing y equals a over x, I'm going to write t equals a over n. Because again, t is my output, n is my input. Now they gave me a n value of 10 and a t value of 8, so we have 8 equals a over 10. And then I've got, for my a value, it looks like 10 times 8 gives me 80. So I can rewrite this then as t equals 80 over n. And now they want us to plug a bunch of numbers into this basically and write a table. So let's go through and do that. Here's a table with my 15, 20, 25, and 30 n values. And let's plug each of these in. So 80 over 15 is whatever it is. We could reduce it, I guess, by 5s. That would give us 16 over 3. 80 over 20 gives us 4. 80 over 25 is going to give us 16 over 5. And then 80 over 30 is a little bit easier. That's going to give us 8/3. So what's happening to the time it takes to build a playground as the number of volunteers increases? Well, if we want to be really general, we could say that as n goes up, t is going down. If you look at these values here, this is like 5 point something, 4. This is like 3 point something. This is like 2 point something. So definitely as volunteers increase, time to build decreases. Now we could be a little bit more specific, and if we kept going, we might notice that we were decreasing our time by less and less each time. In fact, if you wanted to just take a quick look at what this looks like on Desmos, let's write this as y equals and then a fraction 80 over x. And it's kind of hard to see what's going on, but if we zoom out and just look at the positive values, because we don't want negative volunteers, right? If you look at as the number of volunteers increases, like the time, which is this y value, the time to build the playground is definitely continually decreasing, but it is kind of leveling off. And in fact, we can't get down to a time of 0. We can't build it instantaneously no matter how many volunteers we have. So anyway, that's kind of neat. And at this point, we are out of time, both for building playgrounds and for talking about inverse variation. Until next time, Mr. Sutton signing off.